Hi, this is David, and in this installment we'll try to show how the various biological conceptuses result in the placental morphology that we see. So beginning with dizygotic twinning, there are two acts of conception where a separate sperm fertilizes a separate egg for each twin. In that case, it gives rise to two different embryos, two different zygotes, two different embryos, two different blastocysts, and therefore you get two different fetuses, each with its own gestational sac. But what subsequently happens to those gestational sacs varies. So in one scenario, the gestational sac could be entirely separate. So in this illustration, white is amnion, that's why it reflects off the placental disc. This is the placental disc here that's shown as the ovoid figure. So here the amnion reflecting up. So and the green will be the chorion, and it goes entirely around the disc and the membranes. So in the first scenario, the two twins are entirely separate, non-contacting, and you get two placentas with their own gestational sac, and they're not touching each other. So you have separate discs that are not in contact. The next scenario that you could get in dizygotic twinning is that they're predominantly separate discs. The two placental discs that I'm showing you here, the placental discs are separate. The amnions in white are clearly separate. The chorions in green are separate, but the membranes that I'm showing here touch or fuse at one point. So it's just contact or fusion of the membranes. And clearly, if you could imagine what you would see here at the area of fusion, if you took a section here where I highlighted in red, you'd see the amnion of twin A if this is twin A, you'd see the amnion of twin B if this is twin B, and you'd see the chorions of the two twins respectively, and sometimes the chorions sort of fuse together, but at the point of contact. So that's what you would see. But they're really still separate placentas, only with an area of membranous fusion. And in the last scenario, the discs actually fuse, and when they fuse, they create a bit of a fibrin ridge on the disc surface. That's sort of at the point where the two discs fuse. And the discs are fused, and this is, let's say, twin A, and this is twin B, and this is the amnion of twin A and the amnion of twin B. And each twin has their own amnion and own chorion. The discs have fused, and there's a dividing membrane in between the twins that I'm showing here. So the twins are being nourished by a common placental disc, or a fused placental disc. I shouldn't say common, by a fused placental disc. And they're divided by a membrane that includes both amnion and chorion contributed by each twin. So it would still again look like this. So twin A would contribute amnion and chorion, and twin B would contribute amnion and chorion. So it would be a fused diamniotic dichorionic placenta, and that again would be compatible with a dizygous pregnancy. So once again, for dizygous pregnancy, you could have two different fetuses with gestational sacs, and they could either stay separate, fuse at the membranes, or fuse at the placental disc and at the membranes, and then you just have this dividing membrane. And the dividing membrane will be diamniotic dichorionic. So diamniotic dichorionic. Now let's look at the scenario of a monozygous twin. In monozygous twinning, there's a single act of fertilization, so one sperm fertilizes one egg. That then leads to the two-cell embryo stage. The first scenario here is that splitting could occur at this stage. If splitting occurs at this stage, then each separate blastocyst goes its own way and gives rise to its own embryo. Then what usually happens in monozygous, theoretically you would say, well, since I've got two entirely separate embryos, I could probably have all three of these scenarios. But because they've biologically arisen from two cells that were compacted together in the same blastocyst, so there's a splitting of the blastocyst at the two-cell stage, because that happened in two cells that were in very close proximity, usually what you get is just this scenario. So the same as this scenario. So you get a diamniotic dichorionic twin placenta. So what you realize now, or what you should realize now, is that for the diamniotic dichorionic twin placenta, And once again, let's look at the dividing membrane. The dividing membrane has amnion and chorion contributed by A, and amnion and chorion contributed by B, and this is what the dividing membranes look like. So you realize that for a diamniotic, dichorionic twin placenta that we call a di-di, it could either be monozygous or dizygous. If the membranes are completely separate and non-fused, it's usually dizygous. So that non-fused would have to really be dizygous. But if you have a diamniotic, dichorionic twin placenta, we've already seen, even already, that it's compatible with both the dizygous and monozygous scenario. So I'll just tell you that most di-dis, most diamniotic, dichorionic twin placentas, are actually about 75% of them are usually dizygous, and only 25% of them are monozygous. But let's carry on. So the split could occur very early, and it could result in a diamniotic, dichorionic twin placenta. The other possibility with monozygotic twinning is that growth continues, and you form your blastocyst, and you get to this sort of stage where the embryo forms an outer cell mass and an inner cell mass. And in this stage, you will get two entirely separate inner cell masses, but with a common outer cell mass. And then these inner cell masses will then go on to form an amniotic cavity. There'll be amniotic gestation. Each one will form its own amnion. Each one will form its own yolk sac. But you could see the outer cell mass gives rise to the chorion. So this entire structure will be surrounded in a common chorion. So green here is chorion. So in this scenario, the twins are surrounded by a common chorion, but as we said, each inner cell mass gives rise to its own amnion, so that each twin has its own amnion. So they have their own amnion, but they share a chorion. And that's why we say diamniotic, monochorionic. And if you take a section of the dividing membranes, what you see is an amnion from twin A, an amnion from twin B, but no chorion in between. The last scenario is where the inner cell mass has already started to form its amniotic cavity. And so the amniotic cavity has already formed, and then at that point, the inner cell mass sort of forms two fetuses. It forms two babies. So for those of you that are embryology inclined, you have formation of two separate bilaminar discs, and then two separate gastrulation, but the amniotic cavity is common, and even the yolk sac may be partially common. And so what you'll find in this scenario, which is quite rare, I'll just draw the fetuses in, is that you have two fetuses that share common amnion, obviously a single common placental disc, and a common chorion, and this is what they call a MOMO, or a monoamniotic, because there's only one amnion and one chorion, there's no dividing membranes. Monoamniotic, monochorionic. And just as a clinical tidbit, because there's no dividing membranes whatsoever, this specific scenario, the monochorionic, monoamniotic twin, is at risk for cord entanglement. So the umbilical cord could entangle. And that's a serious complication, and it could be devastating in monoamniotic, monochorionic twinning, and it's one of the reasons that monoamniotic, monochorionic twinning is dangerous. But the other thing to point out is, so when the pathologist is looking at a placenta, the pathologist either encounters two entirely separate twin placental discs, which is obviously diamniotic, dichorionic, and then you could surmise pretty well that it's most likely a dizygous pregnancy. And if you have monoamniotic, monochorionic, or diamniotic, monochorionic, in these two scenarios, you know that it has to be a monozygotic gestation. Where the pathologist can't tell is with a fused single placenta, which is diamniotic, dichorionic, because that could either be dizygous or monozygous gestation, and one would need further studies. Now, obviously, if one's a boy or one's a girl, then you would know that it's dizygous. But if it's equal gender, diamniotic, dichorionic, single disc twin placenta, that's when the pathologist can't tell. So just as another tidbit, we mentioned that the monoamniotic, monochorionic twin placentas were at risk for cord entanglement. It's actually the diamniotic, monochorionic, single disc twin placenta that's at risk for twin-to-twin transfusion. So this is is the scenario which is at risk for twin-to-twin transfusion, the DIMO twins. The other last detail that I'll just mention, it's an interesting tidbit, is sort of we mentioned that the later and later division, the less there is separating the twins, and the extreme of this, people would say, although there's some dispute, is when you actually have conjoined twins. And one fact that we know, but nobody sorted it out, is that we know that already in monozygotic twinning, there's a female predominance. So for whatever reason, monozygous twinning, splitting, is more common in a female conceptus. And the further the split occurs, so in other words, the closer the twins are, the less the division. So as you progress from diamniotic dichorionic monozygous to diamniotic monochorionic, obviously monozygous, to monoamniotic monochorionic, as you progress to a later and later split, the female predominance also becomes more marked. So at this point, your XX chromosome is even more dominant, and I believe in conjoined twins, by the time you get to conjoined twins, there's about a 70% predominance of females. But nobody really knows the reason for that. There's a lot of speculation. Some people say that it has to do with X chromosome lionization, but I just leave that in as a point of interest and curiosity. So that'll be the end of this module.